Hi there, my name is Sky Chalmers. I'm a Westfield State biology major. This past semester, I have had the pleasure of working with neuroscientist Dr. Robin White on Drosophila melanogaster, developing a novel scopolamine-induced Alzheimer's model. To begin with some background, Drosophila melanogaster have been demonstrated to be an extremely useful model when researching neurodegeneration in the brain, or when cells in the brain begin to deteriorate and cause clinical symptoms, including functional impairment, as well as behavioral and psychological declination. More specifically, their nervous systems represent important parallels to the human nervous systems. The blood-brain barrier, a microvascular layer that surrounds the brain and protects it by strict permeability, is present in Drosophila and is a very important structure to incorporate in drug research when modeling mechanisms of treatment delivery across the blood-brain barrier. Previously, their use in studying Parkinson's disease, Huntington's disease, and traumatic brain injury have given us good reason to think it would also be a great model for Alzheimer's disease. Alzheimer's disease affects roughly 11% of Americans over the age of 65, so far without treatment that halts the neurodegeneration of the brain. Current treatment only manages to dull the outwardly visible symptoms of Alzheimer's disease, and until new research emerges, it will remain to be the case. Personally, I have an interest in studying Alzheimer's because I worked as a certified nursing assistant for 4 years on an Alzheimer's dementia unit. And the devastating effects of the disease on both the individual and their family members is just heartbreaking. Therefore, my piqued intrigue at the opportunity to study it in an animal model. So, Dr. White and I set out to find ways to model Alzheimer's disease and proposed a scopolamine-induced Alzheimer's disease model in Drosophila. Previously, scopolamine hydrobromide, whose molecular structure is shown here, has been demonstrated to elicit Alzheimer's-like presentation in other animal models such as mice and rats. This is due to its characteristic blockage of acetylcholine receptors that cause the appearance of cognitive amnesia and electrophysiological changes in the brain. However, where these models share only a fourth of the human genome, Drosophila share a whopping 60%. Due to this parallel in the human genome and the previously mentioned parallel in the human nervous system, we determined that Drosophila may be a more appropriate model for this psychopharmacological model of Alzheimer's disease. To test our hypothesis, we optimized a treatment dosage and then monitored the locomotion and survival of male wild-type Drosophila melanogaster. They were kept in transparent fly houses supplied with formula 424 instant Drosophila medium and supplemented with 5 to 10 granules of dried yeast. Flies were kept in a 12 to 12 light-dark cycle. Since the scopolamine-induced Alzheimer's disease is novel in a Drosophila model, we had to develop a dosage protocol to determine appropriate dosages that would allow for progressive development of Alzheimer's-like presentation while still maintaining a reasonable survival period for sufficient data collection and analyses. Here, we use scopolamine hydrobromide purchased from Sigma, beginning at higher doses, and then reduced and narrowed our treatment dosage range to an appropriate working dosage. The food medium in fly houses was wetted with 12 milliliters of varying molarities of scopolamine solution, which was not replenished after first administration. The rapid iterative negative geotaxis, or RING, assay is used to assess the decline in locomotion function, a symptom commonly associated with the progression of Alzheimer's disease. RING was performed daily, where still images were taken 3 seconds after 3 successive vial taps, meant to move the flies to the bottom of the vial and elicit an upward climbing response. Baseline analysis was performed pre-treatment and then daily post-treatment. The assay was repeated 5 times per treatment with 30-second rest intervals, and we used ImageJ software to quantify the differences in the height climbed. The last thing we assessed was survival, and that was measured daily post-treatment by counting percent of flies surviving. Experiment 1, survival to the left, demonstrates 100% death by day 2 in treatments where scopolamine dosage were equal to or above a concentration of 10 millimoles. Experiment 4 to the right utilized lower dosages of scopolamine, where survival demonstrates a progressively tapered decline in survival in all groups from day 7 to day 10 of the experiment. Experiment 1, ring analyses on the left, shows high-dose treatments of scopolamine experience a marked decline in motor function on day 2. Experiment 4, ring analyses on the right, shows a much smaller but progressive decline in motor function, where controls and 1 millimolar dosages outperformed 2 and 2.5 millimolar dosages in most assays represented here. So, higher dosages utilized in experiment 1 were not feasible for analyzing model decline, as mortality was 100% within the first 2 days of the trial, so not enough time to get the information that we needed. Optimization was necessary to determine a proper dosage concentration. Experiment 4 used much lower dosages, increasing survival length that produced a broader data set. This allowed us an appropriate assessment of motor function decline, which does show a slightly decreasing trend after scopolamine treatment. Experiment 4 data did not show marked differences between treatments. However, there is a notable difference in motor function and survival among the 2 and 2.5 millimolar treatments when compared to the controls. This model has never been attempted in Drosophila, and with further research seems it would prove promising as a model of the pathogenesis of Alzheimer's disease, as demonstrated here. In future direction, assessment of short-term memory merits investigation to properly associate this scopolamine-induced model with a relevant Alzheimer's disease clinical presentation. A courtship assay is a great way to measure short and long-term memory in Drosophila, as demonstrated in its previous uses. Here, a courtship chamber is pictured with male wild-type Drosophila and freeze-killed pre-mated females. Here, males are conditioned in a housing block by repeated rejection of the pre-mated females. The ultimate test is to determine whether or not the males remember the rejection experienced during conditioning, which occurs because a female is less likely to engage in courtship behaviors when they've already had a mate. Courtship behaviors are normally described as males orienting, following females, wing tapping, licking, and attempted copulation. Males exhibiting neurodegeneration are expected to forget their conditioning and therefore attempt to court the female, while a neuro-intact male is expected to avoid courtship. Thank you so much for watching my presentation. I hope to meet some of you at the Mass URC conference. Please don't hesitate to contact me with any questions about research and any future research I could see being conducted. A huge thank you to my faculty sponsor and mentor, Dr. White. Her intelligence support really made my research possible. Thank you so much.